In this video, we'll define the rank of a matrix, and then we'll talk about the rank theorem, which relates the dimensions of the column space, row space, and null space of a matrix. So first we'll define a few terms. The rank of a matrix A, denoted rank A, is the dimension of the column space of A. And the nullity of a matrix A is the dimension of the null space of A. Before I state the rank theorem, let's go over a quick example. Here we have the matrix A with entries 1, -1, 2, 7, -5, -2, 2, 1, -4, 0, 3, -3, -2, 5, 1. We are asked to find a basis for the row space of A, column space of A, and the null space of A. When we row reduce A, we get the following reduced row echelon form. So a basis for the row space of A are the non-zero vectors in the row echelon form of A. So here the basis consists of vectors 1, -1, 0, 3, -1, and 0, 0, 1, 2, -2. To find a basis for the column space of A, we look at the row echelon form of A and identify the pivot columns. They're the first column and the third column. So the first and the third column of our original matrix form a basis for the column space of A. Those are the vectors 1, -2, 3, and 2, 1, -2. Lastly, to find a basis for the null space of A, you want to write the solution to the homogeneous equation A times x equals 0 in parametric vector form. Looking at the reduced row echelon form of the matrix, we can translate the rows into equations. We have, for the first row, x1 minus x2 plus 3x4 minus x5 equals 0, and x3 plus 2x4 minus 2x5 equals 0. So the solution to the homogeneous equation A times x equals 0 is the vector x consisting of entries x1, x2, x3, x4, and x5 equals x2 minus 3x4 plus x5. x2 is just x2. x3 is -2x4 plus 2x5. x4 is x4, and x5 is x5. Separating the vectors according to the free variables, we have x2 times the vector 1, 1, 0, 0, 0, x4 times the vector -3, 0, -2, 1, 0, plus x5 times the vector 1, 0, 2, 0, 1. So these three vectors here form the basis for the null space of A. Now that we have a basis for the different subspaces, we can figure out their dimensions. The dimension of the row space of A is 2. The dimension of the column space of A, or the rank of A, is also 2. And lastly, the dimension of the null space of A, or the nullity of A, is 3. So now let's look at the rank theorem, or sometimes known as the rank nullity theorem. So the theorem states, let A be an m by n matrix. The first part says that the dimension of the row space of A is equal to the rank of A, which is the dimension of the column space of A. The second part says that the rank of A plus the nullity of A equals n. We can see from our example that both of these hold true. In our example, the dimensions of the row space and the column space are both 2. Also, the rank of A was 2 and the nullity of A was 3. They add up to 5, which is the number of columns in my matrix. So let's see why each of these statements are true. The rank of A, which is the dimension of the column space of A, is equal to the number of pivot columns in your matrix. Now we have a pivot column for each leading entry in our reduced row echelon form. And the number of leading entries is the same as the number of non-zero rows in the reduced row echelon form of the matrix. And the number of non-zero rows is the dimension of your row space. For the second statement, we know that the rank of A is the number of pivot columns. And then the dimension of the null space of A, that's the number of free variables you have, or the number of non-pivot columns. Therefore, the sum of the number of pivot columns and the number of non-pivot columns should equal your total number of columns, which is n. So that's the rank theorem. It relates the dimensions of the row space, column space, and the null space of a matrix. And that's where I'll end this video. Thanks for watching.